Thank you so much. Thanks for the introduction, but I need no introduction. I am the most underrated Twitter account. So yeah, that means you're not following me, so please go follow me. Seriously speaking, I am part of the Anza performance team. There are 5 of us now working full-time on performance, which should tell you how serious we are about perf. And as many of you know, I am Italian, and I am intense, and I get upset very easily. And I get very upset when people say this thing. So many people, especially on crypto Twitter, are very confused. They keep saying that we've reached some imaginary limit of scalability. People are working on L2s, L3s, L4s. It will never end. And instead, what I think is that we just have bugs. And bugs are easy to fix. Once we find the bugs, we fix them, and we get so much faster, okay? Speaking of confused people, this was Tolly himself. After the 1 million TPS demo, I ran into him, and he was like, oh my God, there's VM so fast. It's just that we suck at writing networking code. And I agree, but who's we? So what I want to do today is I'm going to show you some of the biggest bugs we have. The goal of my talk is to show you that once we fix these, we scale a lot, like several multiples of where we're now, right? So before I do the analysis on what we're looking at here, let me give you a little primer on how a profiler works. So here on the left, you see thread names. So Sol Repair SVC is one thread, Sol Repair Listen is another thread, and so on. What you see on the right is what the threads are doing while they're getting profiled, right? So when you see a gray area in the timeline of a thread, that means that the thread is doing user space stuff. So it's executing agave code, right? When you see yellow, that means that the code has done some kind of syscall, and now we're executing kernel code, okay? Generally speaking, when you see a little yellow code, it's already bad. So like if we look here in Sol Repair Listen, there is some yellow here, see? This is usually bad, because it means you have some overhead, and you're wasting some time doing kernel work instead of executing the logic in user space, the on-chain logic, right? When you see this amount of yellow, it means that it's a disaster, okay? It means that just things are not working, okay? What this yellow is so the goal that we have is to, my personal goal, I want one thing in life, and I want to double block space, and I want larger transactions, right? So we've been running some stress tests on Agave to see on whether we can do that. Because we know, we do know that the virtual machine is fast, so we can do a lot more throughput. We know that we can ingest many more transactions than what we're ingesting now. We saw during the Trump coin launch, we did several multiples of the kind of traffic we're ingesting now. And we had no problems. We had some congestion, but it was like in later layers. They were at the scheduler layer. But TPU-wise, we ingested a truckload of transactions, right? But Turbine, we knew that Turbine was not going to scale. And so we set up this experiment in which we have essentially simulated a cluster of 5,000 peers. And so what you see here is what happens to an Agave node when it's the root of Turbine and has to retransmit to a lot more peers than we retransmit to today. An amount of shreds that is like multiples of what mainnet beta produces today, right? And what happens essentially is that, like, if we go to the Sol win insert thread, which is the thread in Turbine that ingests the shreds, and we see some markers that I created in my profiler to see how quickly the blocks come in. You can see that this block took 600 milliseconds, this one 800 milliseconds, this one 700, this one 900. You can see that the blocks, they all overlap because they're late. They get late because Turbine is slow, and so we're not fast enough to propagate the shreds, and so everything stops working, essentially, right? And so as a result of this, if we go to repair, we see that in 18 seconds, we generate thousands of repair requests. We're essentially repairing all the shreds because they're all late, so we don't see them, and so we start repairing. And you can see the repair listen thread, which is what listens for repair responses. starts spiking, and essentially nothing works anymore, okay? So if we see why this is happening, so I'm going to select the sol retransmit threads. We use 12 threads right now to broadcast the shreds in Turbine. If we see what those threads are doing while we're running this stress test, they spend about 25% of the time calling this get retransmit addresses, okay? This is the infamous Turbine shuffle thing. For each shred, we shuffle the Turbine tree, and then we find the next peer we have to retransmit to, and then we do the retransmit. This in itself is very slow. Personally, I think it's debatable on whether we need to do this at all, but we're doing it. We can make it a lot faster by switching from cha-cha 20 to cha-cha 8, so doing fewer cha-cha rounds. That gives us like a third speed up. But the vast majority of the time is this yellow stuff, okay? And it's the send multiple message syscall. So what we do is we get the shreds, we get the list of peers we have to retransmit the shreds to, and we send them, right? We do this send in batches because we want to reduce the overhead of each individual syscall, so we do it in batches. But at this packet rate, and the packet rate here is like 2.5 million packets per second. So it's like orders of magnitude more than we do in mainnet today. Essentially, nothing works anymore. We have a whole bunch of overhead. We end up doing all this work when the work to actually queue the packets inside the network card is this 10% I'm highlighting here, okay? So this is the work we want to do, but because of the way we do it, instead of doing it with like 10% of the runtime, we have all this extra overhead. This extra overhead includes this schedule syscall called inside the send message syscall. I did a bit of digging in the history of the Linux kernel here, and this is a mitigation that was added 19 years ago when the scheduler was not preemptible. And so it was a way to stop one single process from monopolizing the network card, essentially. So they went in there and they said, okay, every few packets, schedule out and like give a chance to other processes to send packets. So we're paying this 24% tax for something that someone did 20 years ago, right? There's no reason why we must pay this. And then there is this other large chunk, which is about 11%, which is essentially just allocating some internal data structures that the kernel uses to push the packets inside the network stack. And then my favorite, there is this NF hook slow. This is net filter, okay? So even though on these nodes I have no IP tables rules added to the tables, we still pay this huge tax. I mean, to be fair, in fairness, it is called slow, right? So they know that it's slow, right? But we're doing all this work for nothing. Like, we don't need to do this. So when I saw this, it became clear to me, okay, what we want to do is this. And I went on a journey. First, I wrote an IOU ring-based implementation of Turbine. It was much better than this, but it was still not good enough. And then I went a little autistic and started patching the kernel to make IOU ring faster. And then after a week, I was like, okay, I need to do something else. And so I did this. I wrote an XDP-based implementation of Turbine. And to show you how it works, if I do the same thing as I did before, if I select the sol win insert thread, and I show you how the blocks are doing, the blocks are all nice and under 400 milliseconds, right? There is not one single late block. And here we're pushing 2.3 million packets per second, okay? So this is like orders of magnitude more than what we do in mainnet today. And what's even better is that if we go back to the previous profile, we have these 12 threads I showed you, right? These threads are all cranking at like 100% CPU, meaning they are using 12 CPUs to do the retransmit, right? Agave gets so overwhelmed while we do this that if we look at the POH thread, the POH thread is just hashing, right? Non-stop. So it should always be at 100% CPU. But the machine gets so overloaded that POH stops because the scheduler just doesn't have CPUs to schedule the CPU thread on, right? Literally nothing works anymore. And instead, when we do the XTP-based one, we do all that work that we were doing from 12 cores on one core, one single core. And this core is sleeping for the majority of the time. So there is so much extra capacity. We can send so many more packets, right? In this test, we were saturating 25 gigabits per second, but I have tested up to 100 gigabits per second, and I'm waiting for someone to give me access to a NIC that can do 200 gigabits per second, so I can test that as well. So bug fixed, we can scale now, okay? Now, I'm going to show you something else. Brendan mentioned before that skip rate is about 0.5% right now. It's great, because it used to be so much higher. When we got congested at the beginning of last year, I was debugging some high-stake nodes, and those nodes were like at an extremely high skip rate because they got hit. They had many leader rounds, and so they got hit with a lot of traffic. The one I was debugging on, a foundation node, had up to a 30% skip rate. Okay, so things have improved massively since then. But we still have this 0.5%, which is not nothing. It's annoying, right? You know, like we shouldn't be skipping any blocks, right? One case where we know that we always skip blocks is at the Epoch boundary, right? So this is a profile of the Epoch boundary. And as you can see here, we are replaying slots, and then there is this happens. For nearly 2 seconds, we don't receive anything on Turbine. Replay is completely stalled. It's not doing anything. And then at some point, we get this weird little guy, this block that is like 68 milliseconds. What is that? So we got that block, but look, replay, the replay thread, you still don't see any green here. It means that replay is still blocked, not replaying that block until this point, until almost 1 second later, okay? The reason for this is that, you know, this used to be so much worse. This used to take like 30 seconds at the Epoch boundary. It was just horrible. Then we implemented partition rewards, which mitigates the issue. But it turns out that when we implemented partition rewards, we started doing this thing. We create a whole pool of threads to generate a data structure that we need to implement the partitioning. And we use so many threads because we thought, oh, you know, multiple threads, parallel, fast, right? But look at this. Look at what's happening here. If I select all these threads and I show you what they're doing, let me select it. So many. The work that is happening in parallel is 4.5%. So like we created this whole thing because we wanted to do it in parallel and fast, and we're only executing our code for 4.5% of the time. The rest of the time, it's contention. We have created so many threads, they're all making each other slow, right? They're all locking each other, and so what we want to happen is not happening. And so what's good about this is that once we fix this bug, it's literally one bug. At the Epoch boundary, we stop skipping blocks. And so we solved the last huge problem we have with skip blocks. This is happening in 2.3, okay? If Trent lets me. I wanted to show you something else, but I'm running out of time. But is Andrew in the room? Andrew, I asked you to do that scheduler fix, the POH fix, right? And I am happy to report that it works. The scheduler is like 50% faster now because you did a great job. Yeah. Okay, I will not be able to show you this because I'm running out of time. If you want to see more profiles, when I publish a profile, usually after I get DMs from people asking me how they can contribute or like, you know, if there's something they can do to help, yes, you can. Find me, and I will find you stuff to do, and then you send me PRs, and everyone is happy. Thank you so much.